All right, so we're going to go ahead and pick back up here then at our last example for this section. And we're going to start to take a look here at example number 3. Can I find the exact volume of the solid that lies inside this sphere, above the xy plane, and below the half cone given by z equals the square root of x squared plus y squared? Okay, what you gotta love about these problems is that they clearly are communicating some solid, and you have almost no ability to visualize what they're talking about. I'm going to encourage you so much to go to the 3D plotter and to try to practice using these things. Again, I'm going to go ahead and immediately jump to that 3D plotter. I already have kind of typed in here exactly what I'm looking at. You can see kind of the sphere, my x squared plus y squared plus z squared equals 4, giving me my sphere shape. Notice that you can click on this button here, the magnifying glass, to kind of make these see-through, so it's a little bit easier to try to visualize what's happening. But we wanted to be inside of this sphere, so we can see that the sphere is kind of creating a wall we have to stay inside of. We wanted to be above the xy plane, so I kind of changed my z-bound there to be 0. I don't want to go below the xy axis, or xy plane, excuse me. And I wanted to be underneath, it said, the cone. So I wrote in the square root of x squared plus y squared, and I get this kind of cone shape. So you can see that there's kind of like this ice cream cone shape that's occurring in here, and that's space that we don't want. Like, we want to definitely be on the inside. We want to be, you know, inside of these regions over here, but not inside of this region. That would be bad. So this is a really awkward region, and you can imagine how difficult this would be to try to find if we were trying to communicate a floor, ceiling, front wall, back wall, like we did back in 4.5 when we introduced triple integrals. That's super difficult to do because the ceiling changes based on what points you're at. Like, you know, if you're standing really close to the origin, then maybe the cone's above you. If you were to reach up, you could touch the cone. If you're standing all the way out here near 2 and you reach up, you touch the sphere. So like the floor is the same, but the walls keep changing, the ceiling changes. It just gets really confusing. But with spherical coordinates, this can be really, really easy to tackle. Let's take a look at how we would do it. Okay, so I'm going to go ahead and think really quickly about that cone shape that I'm like not really interested in, just so I can have at least some visual here to tie back to. So we know that we have this cone type shape, okay, and on top of it, there's this like sphere. So we have this ice cream cone, right? So we got something up there. Now, again, that's not exactly what the picture looked like, but this is something. And what we wanted is all the space kind of around this, but still inside the sphere. So what we're going to be taking a look at then is how we could start to describe the solid E of what we do want, and then how can we start to put some bounds on it. Okay, so here's what we have. I'll say we want the volume of E, which has x, y, z coordinates for their points, and we can clearly see what things we want. We want to be inside of the sphere, so that would require that x squared plus y squared plus z squared less than or equal to 4, because you could be at the edge or you could be inside. Let me rewrite my z squared there. It looks a little ugly. Okay. We could also potentially have the case that, again, z's got to be greater than or equal to 0, because we got to be above the xy axis. I'm going to redraw this picture in just a moment. And then the last thing that we would want is we want to be below this cone. So that would mean that I'm equal to the cone, that I'm on it, but I'm okay if I'm less than it. And again, I'll redraw a picture of this cone down here. Okay, so this is at least what we want. And we want to think about how I could begin to start to convert this. I need to figure out some bounds. This is going to be kind of tough, but maybe not too tough. If I take a look at that first restriction, we see that x squared plus y squared plus z squared has to be less than or equal to 4. Well, the moment that that's the case, what can I replace x squared plus y squared plus z squared with that we already talked about earlier in the section? Well, yeah, we should be able to replace it with a rho squared. But that would mean that if rho squared has got to be less than or equal to 4, then that means that rho has got to be less than or equal to 2. Remember, though, we said rho was always positive, so that means that rho has got to be between 0 and 2. We're a third of the way done. We've bounded rho. Now, I can start to think again about holding my arm up and spinning around and creating different sorts of pictures. In this case, I want to be able to go ahead and imagine maybe all the different thetas that I could begin to work with that would help me to figure out how I could point to all the different spots that are inside of my solid. Again, I'm going to go back to this picture to see. If I can see all these different little red points that I've put on here, if I'm standing at the origin, here's me standing at the origin, and I want to look at all those particular points floating around out there, I'm going to notice have to spin completely around in a circle. I'm not dealing yet with which way my arm is facing in terms of up and down, but I'm going to have to spin left to right kind of all the way around. So this seems pretty obvious that theta is going to have to go from 0 to 2 pi to get all of the space that we need. The last and most difficult part is oftentimes figuring out this value of phi. And there's many different ways to do it. I show one way that requires no geometry at all in my notes, but I don't always think that's necessarily the easiest way. So I'm going to take a look here at a more kind of intuitive approach. So again, imagining that I'm this little person who's standing at the origin, if I was holding my arm, again, perfectly vertical, it's got to be straight up in the air, right? So this little guy over here needs to go and have their arm facing straight up. The guy's got a really long arm. Okay, so he's pointing straight up in the air, and remember, that's phi being at 0 radians, 0 degrees. And so right now, he's pointing definitely at points that are not a part of the good space, because those are points that are in the cone. So he kind of has to tilt his arm all the way out until it's kind of in line with the edge of the cone. And I'm not doing a good job of drawing that. But imagine that his arm faced out like this, so it was right at the edge, right, of that cone. Once his arm has been tilted down that far, right, once he's rotated this much, then now he starts to see some good points. And he could continue to rotate all the way until he rotated down to just being perfectly horizontal. You wouldn't want to rotate any further, because then you would be pointing towards things that are below the XY axis, and we don't want that. Okay, so the real trick here is to figure out first, where does my phi stop? It seems like if I rotate from being vertical, 0 radians is pointing straight up, and I rotate all the way down until I'm parallel to the x-axis, how far did we rotate? We would have rotated pi over 2 radians. Okay, so pi over 2 is the angle we want to stop at, because that's, again, rotated from straight up to straight down, or to straight horizontal. But what we don't know is what this kind of diagonal is where we want to start counting points. And so I'm going to attempt to figure that out in the following way. Here's what we might be able to see. So I'll state this. To find phi, we will look for the intersection of the cone and the sphere. That is, I'm interested in kind of this blue circular kind of region here where these two things overlap. I'd kind of like to know where that is, and you'll see why in just a moment. But finding this intersection is really easy, because if you think about finding intersections like you ever did even back in an algebra class, what do you always do with the two equations when you want to find intersections? Well, you would set them equal most of the time, or you would like do substitutions, which here is super easy to do. Because notice that we have x squared plus y squared plus z squared is equal to 4. But if z squared is the same as the square root of x squared plus y squared, then we can start to solve for what this thing is. Notice we're going to end up with, in total, 2x squareds, 2y squareds is equal to 4. And that's going to give me this blue intersection of x squared plus y squared is equal to 2. So that up there is a circle with radius 2. And I'm going to go ahead and actually draw that on there. Oh, sorry, not radius 2, radius root 2. Excuse me. So I have a radius root 2 there in that picture. Now, there's a couple other things that I can determine. First off, this is my angle of phi, right? My guy, if he's standing there, is rotating, his arm is pointing straight up, and he's rotating as he comes down. And I want to kind of figure out how far I have to rotate to get to the edge of that cone. Well, if I only knew one other side of the triangle, I might be able to use some trig ratios to kind of help determine that. Now here it's actually super easy because I know that that slant side over here actually represents what about the sphere? Yeah, it should be the radius of that sphere, which is 2. So you could probably set up a trig ratio that could relate the angle and those two sides of the triangle. So I'll say here, by the drawn triangle, we can see that the sine of phi would have to be equal to opposite over hypotenuse in order to have that phi, in order to have been rotated to hit the edge of that cone. But of course, what angle between 0 and pi could possibly make this work? Well, that's pretty darn obvious because we all love our trig. That's the angle pi over 4. So if I think now about the bounds on phi, I know that if I rotate, this guy rotates from 0 to pi over 4, boom, I'm at the edge of the cone. And then I start rotating from pi over 4 down to pi over 2. And that's where I hit all good points. So bounds on phi should be 0, or not 0, excuse me. We should start at pi over 4 and go to pi over 2. So now that we have this, the setup here is really, really easy to work with. We can see that the volume should be equal to a triple integral over E with 1. Remember, that's how I can get the volume. And then I just have to transform that with spherical coordinates. I want you to go ahead and see if you can write down what that actually is supposed to look like. Just set up the integral first. I'll let you calculate it here in just a moment. But first, just try to set it up. Pause the video if you need the time. Okay, so if I was to set it up, I would do it in the following way. Again, I can think about my 3 integrals here. Remember, I'm going to have to replace that dv with a rho squared sine phi d rho d phi d theta. So if theta comes first, or sorry, rho comes first, that means I'm going from 0 to 2. Then I would go from pi over 4 to pi over 2. And I said pi over 2, but I wrote pi over 4. And then my theta bounds will go from 0 to 2 pi. So this is perfect. This is the setup. Now, I'm going to, again, leave it to you to actually go ahead and do the evaluation and practice that. Again, you can pause the video here to just make sure that you're on track and you understand exactly what's happening. Okay, so this is what I ended up with. I ended up with a final answer of 8 pi root 2 all over 3. Okay, so again, I think this approach is way easier than the approach that I show in the notes. I would encourage you, though, to look at what I have in the printed notes up online, just to kind of compare and contrast. If you decide that you absolutely abhor what I do in the notes there, that's fine. That's why I did something different here, so you could kind of see it from multiple perspectives. Okay? All right, well, that wraps up the ideas of 4.6.2. I'm very much assuming at this point that you will not be very well practiced at this, and so you need to make sure that you try as best you can to go again to those textbook problems, and you really got to try to crank out as many as you can. You're going to come across questions. It's going to be a little bit difficult at first, but it doesn't mean it's something that you can't handle. You just have to go through and try to practice up as much as you can, and before you know it, you'll be dealing with triple integrals in both rectangular, spherical, and cylindrical coordinates, just no problem at all, okay? And whatever questions you have, feel free to email me or see me during our online office hours.